Welcome to Indices 2. This is the second lesson of a three-part series where we will start to look at some of the more advanced indice laws. Last lesson we looked at and discussed the basic laws, and we viewed a variety of examples of how those laws work. Hopefully you managed to download the worksheet and have a go at the starter questions. We'll start by going through the solutions to these. If we look at the top left question to begin with, we can see that it is asking us to simplify x to the power 5 times by x to the minus 2. Now we know, and we discussed last lesson, that if you have the same base, which we do, both x, and we are multiplying, we can simply add the powers. So the answer to this question would have been keeping the base the same, which is x, and adding the two powers. You just have to be a little bit careful here. We need to do 5 plus minus 2. Well, that essentially means 5 minus 2, so it would be 3. The answer to this one would be x cubed. Moving on to the top right question. Here we have 15x cubed y to the power 5 divided by 3x y to the minus 5. We discussed how we can break this down into steps where we can focus on each of the terms individually. So we'll start by focusing on the whole numbers. What does this say? 15 divided by 3. Well, we know 15 divided by 3 is 5. So the first part would be 5. Then we can focus on the x's because they share the same base. Now we saw if there is no base, the base is 1. And that's really useful. We've got x cubed divided by x to the power 1. Well, we saw that when you divide bases with the same, in this case x, you can minus the power. So we're going to do 3 minus 1. So it would be x to the power 2, since 3 minus 1 is 2. Moving on to the y's. They share the same base, so we can apply the same rule, which is minusing the powers. And here, I've tried to trick you out. We've got 5 minus minus 5. So remember, 5 minus minus 5 means 5 plus 5, which would be 10, not 0. So the answer to this would be y power 10. So the final answer is simply that. 5x squared, and if I write it without the colour coordination, 5x squared y 10. Often I get asked, could I write 5y 10x squared? Yes, that is the same answer. We've discussed previously that multiplication is commutative, which means it can be written in any order. Okay, so that would also be correct, but that would be your final answer. Going down to the bottom left, here we've been asked to raise x cubed to the power 2. So we saw that when you raise a power to a power, the rule is to multiply. So this answer would simply be x, the base stays the same, to the power 6, because 3 times 2 is 6. And then the final question that I've put in, as discussed in the previous lesson, most students only get this half correct. The first thing we should consider here is we need to raise 3xy squared all to the power 2. Well, the first thing we should do is fill in that there's technically a power 1 on the 3, and there's technically a power 1 on the x because there is no power written. And where students miss part of this question is we need to distribute this 2 throughout the powers of every term. So we're going to do 1 times by, because we're raising the power to a power, 2, which would be 3 to the power 2. Then x to the power 1, raised to the power 2, 1 times 2 again is 2, so we've got, x squared. And then finally, y squared times by another 2 would be y4. So most students would just get 3xy4 for this, which is wrong, because we have to distribute the squared to all of the powers, and it is remembering that because there is no power, it is actually 1, and we use that. So we're not quite done, because we know, don't we, that 3 squared is 9. So we've got 9x squared y 4. So that would be your final answer. We shouldn't really leave an integer that can be squared as 3 squared. We should make it 9, because we know 3 squared is 9. So that would conclude the starter. Hopefully you managed to have a go at those and get them correct. If you didn't, just review and correct in what you got wrong. And this takes us nicely on to the next laws, which I've put into Indices 2. So the first thing I've written here is laws of indices increase in difficulty by combining all of the laws. So the first thing you need to know is what are all the different laws and how do they work? And then they start to make them harder by combining them. And we'll see this in further examples today. So the next law that you need to know, law 5, is a to the power 1 over n. So a to a fractional power. And remember, this here is just a generic way to write the rule, okay? It's so you can apply it to anything. Some number a, or even a letter, something raised to the power of a fraction, where you've got 1 over some integer. The law states this. You can write this as whatever the integer on the bottom of the fraction, the denominator is the root of a. So you if it is 1 over some number, you do the root of that number given the original base. And again, students always find that confusing, but when you see it in examples, it becomes clear. So if we take that understanding there, where if you have a base raised to the power of 1 over some number, you do the root of the number on the denominator of the base. What would that look like? Well, here I've got 36 in example 1. I've got 36 to the power 1/2. Well, I know from that rule that I can write this as what is on the bottom, providing there's a 1 on top, what is on the bottom is a 2. So I can do the square root of the base, 36. Now, when we do the square root, we don't generally write a 2 there. You can put a 2 there, but generally we know that that just means the square root. Okay, so you can put a 2 there, but you don't have to. And if you map that up to this law that I've written here, the a is the 36, so that goes inside the square root. The n is a 2, so I could write a 2 there, but we just don't. So what is the square root of 36? 6. So the answer to that question is simply 6. If we move on to example 2, again, we've got 100 raised to the power of a half. And what you'll start to spot is the power of a half just means the square root, and that is exactly what it means. The power of a half means that we're going to do the square root of 100. Yeah, we could put 2 there, but not necessary. The square root of 100 is 10. So the answer to that question is 10. Where this law needs to be considered is when it is not a 2. Okay, when it is not a 2, in this case, in example 3, we've got 27 to the power 1/3. Well, it's going to be the root of whatever is on the denominator, which is 3. So we're going to do the cube root of 27. Lots of students always argue, oh, I don't know what the cube root of 27 is. Well, remember, the cube root just means what number do I times by itself 3 times to get 27. Okay, and you can sort of almost guess. If you don't know it, you can guess. Just pick a number. It's always lower than you think. What number would I times by itself 3 times? Well, let's just try 3. 3 times 3 is 9, times another 3 is 27. So the cube root of 27 is 3. So it's always good to go and familiarise yourself with cube roots. Look at your cube numbers up to maybe 5 or 6. But if you're unsure, just pick a number that's quite low and just try. And generally you can find it by logic. Okay, so the answer to that would be 3. And finally, hopefully you're starting to see a pattern now. 16 to the power 1 over 4. Well, 1 over 4 would mean the 4th root of 16, because the 1 means that I need to use this root, and the denominator means that it's going to be the 4th root. And again, I don't know exactly what, well, let's just say I don't know. I do know, but let's just say I don't know exactly what the 4th root of 16 is. But you can sort of work it out. What is a number that I times by itself 4 times and get 16? Well, the logic there states that it's going to be quite a low number. And what number do you know that goes into 16? Well, 2 is a good shout. 2 times 2 times 2 times 2. Well, 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. So from deduction and logic, we can say that the 4th root of 16 must be 2. And again, it's good just to familiarise yourself with the basic cube roots, 4th roots, maybe not even 5th roots. I'll just go up to 4, but just do the low numbers. So 2 to the power 4, 3 to the power 4. Just familiarise yourself with what those numbers are, and it'll make things a lot easier for you. So the answer to that would simply be 2. So that rule there states that if you've got 1 over some number, you are just doing the root of whatever that number is on the denominator. So if we look at example 5, it looks a lot harder, but it's the same. And there's just one extra rule that you need to know here. Well, what do we know to the power 1 over 2 means? Well, we know that means the square root. Okay, simply the square root. And you could put 2 there, but we don't need to. So this says that we need to do the square root of 25 over 100. Now, if you were keeping up with the surds lessons, which I highly recommend, if you're watching this, you should have watched all 3 of the surds lessons that I've put out. We know that we could write the square root of 25 over 100. We could break that down to the square root of 25 over the square root of 100. That is a surds law that we learn. Well, what is the square root of 25? 5. What is the square root of 100? 10. What is 5 over 10? A half. So this whole question would simplify to a half. So what I've done on that step there, where I've gone from the square root of 25 over 100 and broke it into 2 different square roots on top of each other, is a surds law, which if you haven't already, go and watch the surds lessons. So that takes us on to law 6. Now law 6 is very similar, but instead of 1 over, we've got this. We've got a to the power n over m. What does that say? It says we've got some base raised to a fractional power where it's not 1, in this case, it is any number. So what does that mean? Well, that means we do this. We're going to stick to the same rule that we've just seen, which is the denominator becomes the root. So we're going to do the nth root of the base a. And then what this n means is we're going to raise all of that. Once we know what that is, once we've worked out the nth root, we're going to raise it to the power n. So again, we're going to take the denominator and make it our root. So we're going to do the nth root of the base a. And then we're going to take that answer and we're going to raise it to the power n. Now, we've done that for every single example here. But if you look, what is the power we're raising it to? We're technically raising our answer to power 1, which we know just means it's going to stay the same. So we don't do that extra step where when it's 1, we don't need to raise it to 1 because we know it's going to stay the same. So we should be doing that, but we don't because we know it's not going to affect our answer. However, when it is not 1, when the top of the fraction of your indices is not 1, where it's any number, you raise it to the power of that number. And again, looks quite confusing, but when you start to see it in examples, it becomes a lot clearer. So let's focus on example 1. This says we've got 9 to the power 3 over 2. What does the law tell us? It tells us we're going to do the nth root, so in this case the square root of the base, which is in this case 9. So the first one we're going to write down is the square root of 9. And again, there's no need for us to put that 2 there, because we know that that just means the square root. And then we're going to raise it to this power, so we're going to raise it to 3. So I'll colour coordinate this for you. So I am just going to put the 2 there for this step, so I can colour coordinate for you. This 2 has come from the denominator. This 3, we're raising it to the numerator. And then this simple BIDMAS to work this out. What we're going to do is we're going to say, right, what is the square root of 9? The square root of 9 is 3. And then we need to raise that to the power 3. So we're going to take the square root of 9, which is 3, and we're going to raise it to the power 3. Okay, well, what is 3 cubed? 3 times 3 times 3. 3 times 3 is 9, times 3 again is 27. So the answer to this whole question is simply 27. And the more exposure you get to these examples, the more you'll see the pattern. Example 2 says we have got 27 to the power 2/3. Using that law, it states that we need to do the third root, the cube root of 27, and then raise it to the power 2. So we're going to write that. We're going to do the cube root of 27, and we're going to take that answer and we're going to raise it to the power 2. So again, we're raising it to the power 2, and we're going to do the third root. So whatever's on the denominator is your root, whatever is on the numerator is what you raise your answer to. What would that give us? Well, BIDMAS tells us to do the brackets first. The cube root of 27. We've just seen that the cube root of 27 is 3. And the square, we need to square 3 now. We need to square that answer. So 3 squared would be simply 9. So the answer to this question is 9. So we're using that rule and we're breaking it into 2 steps. We're doing the root of the denominator and we're raising the whole answer of that to the numerator. So in this case, the cube root was the denominator, and we're raising it to the power 2. Okay. Example 3. We've got 16 to the 3 over 4 power. Well, what does that tell us? It tells us we need to do the 4th root and then raise it to the power 3. So we're going to write that. We're going to say, right, we need to do the 4th root of 16, and then we're going to get that answer and we're going to raise it to the power 3. So what is the 4th root of 16? Again, logic, you can work it out. What do I times 4 times by itself to get 16? Well, we've looked at it before, it's 2. And what you'll find is, so we're going to do 2 to the power 3. You'll find that all of these questions, they generally use the same numbers because they're not going to expect you to know ridiculously big 4th roots and cube roots and maybe even 5th roots. So they keep it relatively small, which means you'll start to see the same numbers over and over again, which will give you a clear indication of what those are because you'll just be used to seeing them. So we're going to do 2 cubed now. 2 cubed means 2 times 2 times 2. 2 times 2 is 4 times 2 is 8. So the answer to that is 8. So we're going to develop that into example 4 now, where similar to the last question, a little bit more involved. It's a fraction. So fraction raised to the power of a fraction. So first of all, let's think about what does our power mean? What does 2/3 mean? Well, that means, remember, we're going to do the cube root of whatever we've got, and then we're going to raise it to the power 2. Okay. So what does that mean? Well, it means we're going to do this to both the top and the bottom given our Surde's law. Okay. So what we can say is this is going to be the cube root of 27, and then we're going to square it, divided by the cube root of 225, and then we're going to square that. So we've just taken our understanding of this fractional indice, which is the cube root in this case, and then squared, and we're going to apply it to both the top and the bottom of this fraction. Okay, we're going to do it separately. So let's think. Let's focus on the numerator, the top. What would the cube root of 27 be? The cube root of 27 would be, and we've seen this, 3. And then we need to square it. So we've still got the squared bit to do. And then what do you think the cube root of 225 would be? Well, again, logic can help us here. The cube root of 225 is going to be 5. Not 2, I apologise. That should say, confused myself there, that should say 125. Okay, the cube root, so we can just change that. That should be 1. The cube root of 125 is 5. Okay, so the cube root of 125 is 5. So just make sure you change that for yourself. And then we need to square it. So what do we get? We get 3 squared is 9 over 5 squared is 25. So our final answer is 9 over 25. So again, apologies there, just make sure you change that 2 to a 1. I should have written 125, not 225. Okay, so those fractional indice laws, really important. And as you can see, they do develop quite quickly into having to have a really clear understanding of the laws to apply them to complicated questions. What we're going to move on to now is what it says here in our second bullet point, negative indices. Okay, and we're going to see how they can be combined with the fractional indices as well. So we've called this law 7. It says if you've got a base of a and you're raising it to the power of a minus number, we say that we can do this. We say that the law is this is equal to 1 over the original base raised to the original power. So you take the base and you put it over 1. You do the reciprocal. This is called the reciprocal, which means you flip it. A technically means a over 1. If you flip it, you get 1 over a. All you really need to remember is that this negative indice, this negative power, means you do 1 over. Okay, so you might want to just add that note. It means you do 1 over the base to the power n. Okay, so you just do 1 over the base to the power n. And again, can look quite confusing when you're looking at the generic rule that I've written out here. But if we start to apply it to these examples, it becomes quite clear. So what do we have in example 1? We have 4 to the minus 2. Well, what does our law say? It says that you do 1 over the original base to the original power without the minus. So this would say that this 4 is going to become 1 over, because the negative means 1 over, 4 to the original power, which is 2, squared. Well, what is 4 squared? We know 4 squared is 16, so that is technically 1 over 16. So again, the negative power means you do 1 over the reciprocal, and then you just keep everything the same without the negative power. So we move on to the next one. Example 2 says we have got 3 to the power minus 3. Well, what do we know the minus power means? It means we do the reciprocal. We write 1 over, so we flip the 3, because remember, 3 as a fraction technically is 3 over 1, and if we flip that, if we do the reciprocal, we get 1 over 3. Okay? So it's going to be 1 over 3, the original base, to the original power without the minus. Well, what do we know 1 over 3 cubed is, well, we can work out 3 cubed. 3 cubed would be 1 over 3 cubed is 27. Done. The answer to that would be 1 over 27. You shouldn't leave it like this. If you can work out a whole integer, squared or cubed or to the power 4, please do it. Okay? Don't leave it as this. Get it as a integer. Okay, so now we're going to look at how do these negative powers combine with the fractional powers. And this is where you've really got to have deep understanding of both of them. So here we've got 36 to the power minus 1 over 2. So we're going to break this into 2 steps. The first thing we're going to deal with is this minus. What do we know the minus means? We know the minus means that we can write this as 1 over 36 to the original power without the minus. So the original power without the minus is a half, the base is 36. So we've got the negative means 1 over 36 to the half. What do we know to the power half means? Well, hopefully at this point you're thinking, oh, that means the square root. It means the square root of 36. Yeah? The power of half we discussed in law 5 means the square root of 36. The square root of 36 we know is 6. So the answer to this is simply 1 over 6. So we've dealt with the minus power by doing the reciprocal. Then we've dealt with the actual power, which is the square root, which gives us 6. So we can replicate this in example 4. We have got 8 to the minus 1/3. Well, remember, what does the minus mean? The minus means we're going to do the reciprocal. We're going to flip it. So 8 flip technically means 1 over 8 to the original power, which would be 1/3, without the minus. What do we know to the power minus 1/3 means? We know that means the cube root, so that's 1 over the cube root, remember, of 8. And we know the cube root of 8, hopefully at this point, is 2. So the answer to this question is simply 2. And again, you deal with the negative power first by doing the reciprocal, and then you deal with the original power, which we know is a cube. So as you can see, it's building, and it's going to build now into a fractional power with a negative and a fraction itself. So what would that look like? Example 5, we have got 81 over 100 all raised to the power minus 1/2. The first thing we're going to deal with is this minus. This minus states to us that we need to do the reciprocal, which means we need to flip this fraction. So the first thing we're going to do is just flip the fraction. So we're just going to write 100 over 81 to the power 1/2. Because we've flipped it, done the reciprocal, we can get rid of the minus power. And again, just to be clear, we were flipping these. What is 8? 8 is 8 over 1. And if you flip 8 over 1, you get 1 over 8. So we are flipping these, doing the reciprocal of these whole numbers. It's just you need to know that 8 means 8 over 1. And if you flip it, you get 1 over 8. Okay? It's easier to think of these negative powers when you've actually got a fraction given to you, because you simply flip and do the reciprocal of that fraction. So we've done that. We've flipped our fraction, because that's what a negative power means. We've raised it to the power now without the negative. Well, we know, don't we? We've seen an example that the power of 1/2 means the square root. Yeah, this technically means the square root. So we can do the square root of 100 over 81. And we know from surds that we can break that into the square root of 100 over the square root of 81. The square root of 100 is 10. The square root of 81 is 9. You can leave your answer like this. You should notice that's top heavy, so if you really wanted to, you could change that to a mixed. You could say that is 1 whole and 1/9 left over. but both answers are correct. Okay, so the negative, you flip, reciprocal, you then raise it to the power without the minus. We know that a half means a square root, and it means that we can do the square root of that, which can be broken down into 2 square roots, which would give you the answer of 10 over 9. So as you can see, it does develop and become quite involved. Final example. It's example 6. We have got 32 to the power minus 4 over 5. What does that tell us? Well, we should always deal with the negative power first. A negative means that we're going to write the reciprocal. And remember, 32 means 32 over 1, technically. So if we do the reciprocal of that, we're going to get 1 over 32 to the 4/5. Okay, you write the same power without the negative. Then you need to think to yourself, right, what does 4/5 mean? Remember, 4/5 means, technically, we're going to do the 5th root, and then we're going to raise it to the power 4. So you take whatever is the denominator and do the root of that, and you take that answer and raise it to the numerator, which is 4. So what would that look like? Well, it's still going to be 1 over. It's going to be the 5th root of 32 to the power 4. So again, the 5th root. You probably never learnt the 5th root of 32, but what would we times by itself 5 times? And this is how I think about it. To get 32. Well, it's going to have to be quite a small number. And what small number do we know that goes into 32? Well, let's just try 2. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So by just using logic, we can deduce that the 5th root of 32 must be 2. So even if you do not know it, you can sort of work it out on the spot. So the 5th root of 32 is 2, and we need to raise that to the power 4. Well, 4 as the power means times it by itself 4 times. 2 times 2 is 4, times 2 is 8, times 2 is 16. And again, you can see we're just using very similar numbers constantly. So it's going to be 1 over 16, and that would be our final answer. So again, quite involved, but it's just knowing that that minus means you write the reciprocal, in this case 1 over, and that is the key, knowing 32 is 32 over 1, which is a real basic maths law, but students often forget. Reciprocal of that, flipping it, would give 1 over 32. And then from there, you just use your fractional power law. So it's worth going through these, getting your head around them, making sure you can follow what's going on, play it back a few times if you need to. But what I've got for you in the description is lots of practice for fractional and negative powers, where they combine it. Quite a big worksheet, so I definitely recommend that you have a go at those. I'll also link the answers to those. And then I'll also link another worksheet which would be combining all of the 7 laws that we've looked at thus far. Okay, so hopefully you followed along, hopefully you learned something, and there is one more indice lesson for the higher year 9 and the higher year 10 students, which will be where you need to manipulate the base. Okay, so we've seen, haven't we, that all of these laws generally work when you have the same base. So we will explore what happens when these bases are not the same. How do we manipulate it to get them the same? So that will be in Indices 3, and I'll see you in the next one.